For our project, we decided to look into the red ring of death that occurred on the original Xbox 360. We're going to go ahead and take apart an Xbox 360 and um, try to determine the CPU temperature just based on the heatsink and fan specifications. The original Xbox 360 was well known for the red ring of death. It was called this because of the three red lights that would turn on around the on-off button. And when it did turn on, that usually meant that your CPU or GPU had been warped due to high temperatures. And when it did happen, it usually meant that your Xbox was no longer going to work. It was a really big problem when the first model came out and affected over 68% of consoles. It ended up costing Microsoft $1.5 billion to try to recover from this big failure. The purpose of this project is to calculate the surface temperature of the CPU given the heatsink dimensions, fan specifications, and total power consumption. The ultimate goal is to create a model where the heatsink dimensions and fan specifications can be modified to optimize a CPU temperature. And for the power consumption, we'll be using a watt meter, but of course, not all of the power drawn by the Xbox will be going to the CPU. So we're going to assume that 50% of remaining power will go to CPU during the idle period. The remaining power is what remains after subtracting what the fans are taking and what the disk drive should be taking. We're also going to assume that the fans are working at 80% capacity and that the actual CFM through the fins is around 80% of whatever capacity the fans are working at. And this is because if we look at the Xbox, you can see how there is a poor airflow path. There's not really a path for the air to follow, which means that whatever the fans are drawing out, it's not going to be what is actually going through the heatsink. So to start off our experiment, we went ahead and took apart an Xbox and took off the two heat sinks. Since it was old, the thermal paste was cracked and not in good shape, so we went ahead and reapplied thermal paste and then placed a thermocouple right in between the heatsink and CPU. We were careful to just place it on the corner as to not interfere with the heat transfer between the CPU and the heatsink. We were able to run a successful experiment and got results that seemed more than reasonable. For our mathematical model, we used the resistance method and approximated the heatsink fins to parallel plates. So here you can see how we solved for the surface temperature, and it looks pretty simple, but of course we have to include the forced convection in the total resistance, which means we have to solve for a Nusselt number. In our case, we used a Nusselt correlation found by P. Tierstra and M. Jovanovic. They described forced convection between parallel plates and heat sinks, and this model resulted to be very successful. So we went ahead and used that, and with our first results, we were able to calculate the CPU temperature at 58.43 degrees Celsius, which was only 9.1% off of what we measured directly from the CPU. Given that we made those previous assumptions, I would say this is a pretty good approximation of what the CPU temperature should be at. But just in case, we went ahead and conducted the same experiment, but on a different Xbox model. And the reason for that is we wanted to make sure that this model would work for other heatsink and CPU applications. So you can see here that it's set up a lot different. Of course, Xbox didn't want to go through the same situation with the red ring of death, so they definitely revamped the design. So you can see here we just have one fan, we have one heatsink with a copper core, and when the CPU and GPU are combined into one, which actually makes calculations a lot more simple. And when we did calculate it, we used the same model, but in our total resistance, we included conduction between the copper cylinder and the aluminum heatsink, as you can see right there. And we were able to get results within 2.9% of what we measured. Again, not having to make that assumption on how much power was drawn by the CPU, since the CPU and GPU were together, it made the error diminish by that much. So based on these results, we were able to conclude that this mathematical model would be useful for solving for the temperature of the CPU or GPU without having to go out and test new heat sinks. You can do it all mathematically and determine what would be a better scenario. And especially as engineers, we can use something like this to avoid such a big failure as what Microsoft had to go through. So we could use it in electronics and motors and fans and whatnot. So yeah, thank you.